All right. Yes. No. There we go. Okay, that should do it. So welcome to lecture 5. We're going to work today with some old friends, the gradient, the divergence, and the curl of vector fields. And so to recall, the gradient of, let's say, some small f is the vector in which all the partial derivatives of f are denoted separately in their own components, so to speak. So f here is a function, in this case from R3 to R. So this is what is called a scalar field or scalar valued function. It is just one function of 3 variables rather than 3 component functions, each of which is dependent on 3 variables. And for that, we have this gradient that tells you how the value f, the scalar value, changes if you change x, y, or z. And for vector fields rather than scalar fields, for which we use this capital letter and an underscore that are, for instance, from R3 to R3, it could also be R2 to R2. We have the divergence, which I will sometimes denote as this, and I will sometimes denote as that. The inner product between the nabla symbol, or vector with partial derivatives, and f itself. So what is this? Well, this is the sum of the partial derivatives, but then only taking for each component function the so to speak respective partial derivative. So from the first component we take the partial derivative with respect to the first variable, the second component with respect to the second variable, and so on and so forth. And this is called the divergence of f. And we can also talk about the curl of f, which is often written as this nabla and then a cross product with f. And so this is kind of funny notation. So if we have u, yeah.
Yeah, well, this is a question for after you tell me to explain what curl is.
Mm-hmm.
You also provide some graph tools.
Yeah, we will talk about what their interpretations are and so on after I've talked about it. Yeah, so if I have the cross product between u and v being arbitrary 3 vectors, then I can write down this determinant where I put I, j, and k on the first line, and then the components of u on the second line and the components of v on the third line. And that gives me some 3 by 3 determinant, which I can work out. In this case, I actually do this sort of formally exactly the same way. So I see nabla as a vector with 3 components, namely ddx, ddy, and ddz, and f having 3 components, f1, f2, and f3. So if you work that out by just, keeping your head down and not thinking, then you'll see that you get these 2 by 2 subdeterminants where this one, for instance, is the first one. So it's I times this 2 by 2 determinant, which gives you ddy of f3 minus ddz of f2. Yeah, so this is not really a multiplication of one with the other. It should really be seen as taking a derivative of a function. So that's the first one. And so for me, it makes sense to write this determinant with the pluses and minus signs that you know in these determinants in their proper places so that you know you're doing it right. And then you would get, so here you would get minus df d3 dx minus df df1 dz times j, and then plus the third one, df2 dx minus df1 dy times k. That is just legible. Yeah, so I remember it like this because I can understand what nabla cross f is. If I know my definitions of what an outer product is, I can write down the formula from there by first writing down the determinant and then just working out whatever comes out with the rules of the determinant. Yeah, the book doesn't do that. The book likes to write it as a sum of vectors rather than one minus the other plus the third. And so they interchange these two, but then they put a plus there. Right? Of course, this is all the same thing, but I then have to worry myself in my head, what goes where? And I don't like that. Yeah, I don't have a very good memory for all these things. So I just take the definition. This is the definition. And from there, I just work out whatever it is. I still have to think how much you have to remember but yourself and how much I'm going to give you on a formula sheet. I'm not used to working with formula sheets, but in a way, there certainly are things that I kind of do not wish you to remember. So I do wish you to remember that cosine squared plus sine squared is 1. But I don't particularly want you to remember some of the identities which will come later. Yeah.
Okay, yeah. So for example, tutorial 1, there's a question about differentiating or not integrating a third cosine to the power of 3.
Yes.
Then you would, I don't know those. Try to trigonometric equation by heart. Would you please provide those?
If I would ask them, I would provide those.
Okay.
If I don't provide them, then you can be quite sure I won't ask them.
Okay.
Yeah, I have to still remember, I have to get my head around myself what I find reasonable or not. And that is actually on my to-do list for today to kind of make a decision on that. There's a horrible one later on that I'm actually not even going to write down. And so we're just going to skip it. I've never worked with it in my life. And so if I, after 20 years, haven't done it, then probably it's not so useful for you either. So it's clear how to define this divergence, regardless of the interpretation. It's clear how to define this for a function of two variables. You just have x and y, and you sum two things rather than three things. In the 3×3 case, you can write down this curl, but if in the 2×2 case, you can't. At least it's not so clear what is meant by it, because this outer product is really a 3D invention. Yeah, it was something that works for 3D in 3D.
Can't you just take determinants?
Yeah, but so what with what? I have to have three things.
But you
But
can
I-
just take the determinant of 2×2, right?
I can, but then I do not have I could, but that is actually not the right way of thinking about it. So the curl of a vector is itself a vector. And if I would do that if I go to the 2×2, I would not get a vector, I would get a value. Yeah, and so that sounds like the wrong thing to do. And so what you should do is you do get a 2×2, but you have to multiply it by a vector. For reasons that will become a little bit clear later. So if f is a function of two variables, so f1 plus f2, then, so this curl should say something about rotation. And so the idea is that it measures rotation around an axis. And so this axis in the third dimension is what gives this still a 3D picture. So curl F for such a situation is then the 2 by 2 determinant that you would find, so the df2 dx minus df1 dy, this is a value, but now you multiply it with the remaining vector, namely k, which is the z direction. So f itself lives in the plane in the ij direction or xy direction, and so the curl is still a vector, but then orthogonal to the plane. Okay, so why do these things have anything to do? So why these names, perhaps? Why the idea of divergence and why the idea of curl? Where do these names come from? So the divergence, in a way, is easier to think about. So if I have a box, a small box around a point, yeah, you
It's
still.
almost like multiplying by a factor of 1. So the 0, 0, 1, it's like multiplying by 1 basically.
Yeah, but you have two components 0.
Yeah, exactly.
Yeah.
It's like multiplying just a factor of 1.
Yeah, but it's the right factor 1. So there are 3 of them.
Yes.
Okay. Yeah. So if this is a little cube in the XYZ direction, then maybe actually it's even easier to explain it in 2D. Then I would like to get an idea of how much stuff is flowing in and out of this little box. And the divergence of a vector field kind of is a measure for that. And so if something is incompressible, then the amount of stuff that's in this box is always the same, because exactly as much goes out as there is that this goes in. So if I measure the flow of mass in, let's say, the y direction, then it should be countered by the flow in the x direction to have the same stuff in that box. And so that is why divergence free, so divergence 0, corresponds to incompressible fluids. Is this something that you learned in the other course? Yeah. So the divergence is like a flux per unit volume out of a box or a ball around a point. So we know how to do these fluxes. In fact, that was the last lecture. And so, in fact, we can write this divergent in this way. I'm not going to prove it anyway, but I'm just giving you a formula and then giving you an interpretation of what is written on that formula. Okay, so this is a big mouthful, and it's actually not something that I expect you to actually know by heart, but it is useful to see how you should read this. So what is written here is that I have a point P, and around it I make a ball in 3D. I could have done it in 2D, but it doesn't matter. For divergence, it's all a bit the same. And this ball has radius epsilon. So this is my ball radius epsilon. And it has a surface. So the surface is S epsilon, which is a sphere. That's where the S comes from, or surface, I suppose. And the area of this ball, well, that's a standard formula. The area of that, the surface area of a ball of radius epsilon is 4/3 pi, and then epsilon squared. So what you see written over here is that it is 1 over the volume of the ball that I'm integrating over. Yeah, so this is a per unit volume. Whatever is written here, you divide by the volume. What is written over here? Well, this is a formula for the flux of F through the boundary of that surface. Because N here is a vector which everywhere points outwards and is a unit vector. So with that notation, F dot n measures the flux of F through the surface. We have to look at the inner product, the projection, if you will, the inner product between the vector field and the direction out of the surface. You integrate that over the surface, and so what is written here is the total flux of F through that surface. Evidently, if you have a bigger surface, you're going to get a bigger flux. And so you have to counter that by looking at it per unit volume, so that if you take twice as big a surface, this ratio does not change, and it stays constant. And so apparently this is the same as the divergence, which is not so different from this picture that I showed you over here, where stuff is flowing in through a boundary in the x direction, let's say, and out in the z in the y direction in 2D. And if it were in 3D, I would do this with a box, and I would have 3 directions, and I would have to measure how much is going into the x direction or out in the y direction and in the z direction, and the total, if I sum this, is the total stuff that flows over the boundary of that box. Yeah. So this kind of makes intuitive sense. So the divergence measures flux over the boundary of a small ball centered at a point per unit area of that ball. So clearly, yeah.
Now, in the regular calculus, when we talk about divergence, we talk about like the functions sort of split.
Yeah.
And never meets forever.
If they do, so this idea here is that if I have, let's say, a square and it diverges, then the idea is that even if it becomes narrower, it becomes wider. So if the divergence is 0, then the stretching in one is exactly countered by the compression in the other. That is divergence 0. If it is really diverging, so the divergence is positive, then the stretch in one direction really becomes larger than the narrowing. Yeah? That would be that there's more stuff flowing in this direction. There's actually stuff coming in, and so the net result is that stuff diverges. That's where the idea of diverging comes from.
Okay.
At least that's that's the way I think about it. But
but also like divergence in regular calculus, which we learned about it. We had divergence versus
convergence. Yeah, there's no real, so that's really just semantics. So that's English not being able to come up with different words for rather different things.
So
This is a completely different concept. Yeah. So maybe just to put this in a bit of other different perspective, you can see that both of these measures, the divergence and the curl, they say something about what this vector field does in terms of the first order partial derivatives. Yeah. But it's also, you should recall that if you have a function, from R3 to R3, there are 9 partial derivatives. Yeah. dfi dxj, if you will, where I goes from 1 to 3 and xj also goes from 1 to 3 because you have 3 variables, x1, 2, and 3, which we generally call x, y, and z. So there are, in principle, this vector field, if you want to know what it does around a point, there are 9 things you should know. And this is kind of a mouthful. You can put them all in a matrix, and that matrix also has a name. It's called the Jacobian matrix, which appears in many situations. But the divergence and the curl of this vector field kind of summarize some of the behavior of this function, but not all of it. Yeah. So these are useful ways of saying something about the behavior of this vector field, but they are partial information. So because they only use part of all these derivatives, and that's maybe just another way of thinking about why it is useful to have these kinds of measures that do not take all the information into account, but just part of it so that they're still useful in some applications. You had a question.
Yes, so for the formulation before, if the surface doesn't take the form of the sphere, can we technically replace the
Yes.
1 over area?
Yes, the proof is just harder. So it doesn't matter, right? And so the idea really is you just have a surface around that point, and you shrink that in terms of size. And while shrinking, of course, the area goes to 0 and the flux goes to 0 over that boundary. And so you have to keep looking at the ratio between the two to get something that remains a reasonable concept. Otherwise, you get 0 divided by 0. And but just intuitively, it doesn't matter which area you're going to take or which box. It could be just a rectangle, it could be a sphere. Doesn't matter. If you want to actually make a proof, then it's good to take something simple that you can do calculations on. Yeah, but that really doesn't matter. So I always keep the idea of boxes and squares because they are most closely related to the actual derivatives. Yeah, the change in the x direction, the change in the y direction, and so on.
So why did you call it a bowl?
I didn't call it, I just chose a bowl.
Oh, okay.
I could have chosen a box, but
3 over 4 pi epsilon squared, is that 1 over the volume?
that's 1 over the
Or
area,
1 of
the surface area of a ball. Okay, I could have also taken, well, maybe you like that better. Maybe that's actually not a bad idea if I do this next year.
Oh, I'm sorry.
Yeah, you can also just write 1 over epsilon cubed if you take boxes with width epsilon, and then you have another boundary, which I maybe call S prime epsilon of the same thing. And now I take boxes whose
I heard you wrong. I thought you said bowl as in like what you
Oh.
eat cereal out of.
rather than
Bowl.
Maybe
Which is
maybe
what
use
you
sphere.
attach with. Yeah.
I see.
I'm sorry. That was
Good point.
my fault.
That's my accent. A ball. Very good. And then it would not be 1 over epsilon cubed because, of course, that's not the surface area, but it's 6 epsilon squared for the surface area. It's not the volume, it's the surface area. Good point. If you read this, we'll actually see that there's actually another interpretation. Not so much in terms of flux over a boundary, but in terms of a source strength. That's a kind of a in this volume. So the idea is that if as much stuff goes in this volume as goes out, then in this thing, nothing can be created. Because if it were created, then there would be more stuff going out and there would be stuff going in. So this source strength is the idea that some stuff is created at a point. Maybe a force is created by putting a mass somewhere, or some fluid is actually being created because you have made a system where you have an opening and there's just stuff going in. And so that just gives a source of fluid. Yeah.
Yeah, I was gonna say, so it's like a source/sink.
Source of sink, yeah. So this is what you should think of in terms of this source strength. And you can also compute that if you have this volume, let's say D, then this source strength can actually be computed with this divergence integrated over this volume. And if you put the 2 and 2 together, you actually see that if these two things must be the same, then you should get an identity like this, where you can convert a volume integral to a boundary integral. And this actually has a name, and we're going to come back to it in a couple of paragraphs. And this is what's called a divergence theorem. And it is one of the chief sources of deriving partial differential equations in all kinds of applications, so fluid flow, mechanics, electricity, magnetic fields. They allow you to switch between boundary integrals and surface integrals, volume integrals. And then saying, well, the volume is arbitrary, so that means that the integrand is 0, and that actually gives you then a partial differential equation. I guess that's what you have been doing a bit in the other courses, yeah? Okay.
He just took it as a given.
I'm sure.
Right.
Yeah, so we will plug some of those gaps. But I think that some of the physical interpretations were more better explained in that type of course. Well, maybe yes, maybe. Okay. So for example, if I take our familiar friend of the vector field where I put a mass at a certain source, and that gives me this force field. So R here is X times I, Y times J, Z times K. And then I can take the R without the subscript and saying, well, that's the length of this vector. And so then, so that R cubed is actually the length of R cubed, and that makes my writing a little easier. So that means that R squared without the subscript is equal to the length of the vector squared, which is just the sum of squares of all these components. And from here, if you take partial derivatives, so for instance, dr dx, we saw last time, I think, or the kind of time before, that this was x over r. Yeah, because you get 2r dr dx is 2x. And now you rewrite that. And the same goes for dr dy, is y over r, dr dz, z over r. Right, so these are just a few preliminary things that I will need in a minute. And so with it, I can check that this vector field is divergence free, which is something I do not have a particular, because it's a force field, I don't have a particular intuition for. I'm also not a physicist, I suppose. So just to give you the first of these, df1 dx. All right, so f is written in vector notation here. And so I have to take the first component, that's x. And so this is d dx of mx over r cubed. And I also said that's actually the same as, well, m is a scalar, so it's this. But r, of course, depends on x. So I have to do some calculations to work this out. So that's times, and then I have to do the quotient rule. And that gives me that. So the second line, it's x times the ddx of r cubed. So that is 3r squared times dr dx. That's why I needed what dr dx was, and why I first looked at r in terms of x and these partial derivatives that you can derive from them. And so we can say dr dx is x over r, fill it in and work it out. Okay. So that's m times r cubed minus x times 3r squared times x over r divided by r to the 6. If you work that out, it's this. All right, something comes out. Of course, x, y, and z have completely equal roles, and so I don't have to do this computation for df2 dy. It must be m over r to the 5 times r squared minus 3y squared, because I would have to do exactly the same computation, replacing x by y. And df3 dz is m over r to the 5 times r squared minus 3z squared. If you sum these, you get m r to the 5 times, well, you get 3r squared that you have to sum. And then you have to deduct 3x squared plus y squared plus z squared. But that, of course, is also r squared. And so this is 0. I see some nodding heads, as in, I can do this. Good. I will skip the parts on Dirac delta functions. I don't think I'm going to need it later on. And good, you can read it. I don't think there will be any computations with it here. Maybe in 17.4. It's always a bit strange anyway to work with Dirac delta functions. So for the curl, it's a bit harder to get a good intuition for what this thing is, and so it makes sense to do this in an application. So I'm just going to take a simple application where I have a vector field which I now call V, which gives me angular rotation around a point, around the origin. So if you make a sketch of this, it looks like that. And the closer you get to the origin, the smaller. What's happening? Oh. No. I see. So we are Nazis after all, and Russia should also invade us. Hey ho. If I rotate the other way around, would it be better? I guess not. Add extra arrows. I see. So this is this should be a good example to do some calculations on, because this thing has to do with rotation in the plane, and so the curl should mean something that we can think about. And so what I'm going to do two things. Of course, I can just compute the curl that I'll do at the end. But first, I'm going to say, well, let's suppose I take a circle. So C epsilon is going to be a circle around the origin. So the more I draw on this, the better it becomes, right? I'm going to draw this thing around the origin. Actually, I'm going to do this. This point is actually just a general point, x1 naught, y naught. And I'm going to stick with that because otherwise my notes are not the same. And I'll make mistakes. So this is rotation around some point, any point. And I'm going to orient it counterclockwise. And the reason why I want that is that it is easiest to think about it in terms of the parametrization. Because a standard circle that I parameterize with cosines and sines goes counterclockwise. So the parameterization of this thing looks like, well, essentially just cosines and sines. I just have to put everything x naught, y naught away, and I have to make this thing have a radius epsilon. So this is my parameterization of this circle. And I would like to compute one of these circulations. And for that, I need dr, which was a lot simpler than the ds element in surface integrals last week. It was simply the derivatives of these component functions times dt. So this is minus epsilon sinus t dt times I plus epsilon cosine t dt times j. The dependence on x naught and y naught, of course, disappears because these do not depend on t. So with that, I can talk about the circulation of this vector field v around this curve, right? Which I denoted with this integral with a circle around it, through it, v inner product with the length element dr. Well, I've already parameterized it, so I'm going to get an integral from 0 to 2 pi, because t goes from 0 to 2 pi. And then I take the inner product of v, which has these components, with where y is given by that, and x is given by that. So I have to put all of that in, and I have to do that with the inner product with these two. So this gives me omega epsilon minus omega epsilon. Let me put the this is the first one. This is the first component of the vector field, and this is the first component of dr. And I just multiply them. And then I have a second one, omega x naught plus epsilon cosine t times epsilon cosine t. It should just be a few minutes, then we can have a break. All right. So you work that out. Some of these things remain. Some of the cosine squares and sine squares actually disappear because they are 1. And so this is 0 to 2 pi omega epsilon y naught sine t plus x naught cosine t plus omega epsilon squared dt. Well, the sine of t is a periodic function from 0 to 2 pi. If I integrate it, I have to get the antiderivative, which is the cosine or minus the cosine, it doesn't matter. It's also periodic. So if I evaluate it at t equals 0 and t equals 2 pi, I get the same value, and this thing becomes 0. So this thing becomes 0, that thing becomes 0, and the only thing that remains is this. So this is 0 plus something which actually doesn't depend on t at all. So I just get omega epsilon squared times 2 pi. Yes.
Was omega original?
It is the strength of direction. So this is an angular velocity, and omega, if omega is larger, you just go faster. All right, so this was all just some computation in a way, which has to do with integrating the circulation. So now we want to connect it to this curl, and we're just going to compute the curl, this vector field, using the definition. So using this cross product. And so because this is 2D, I can still write it down. It's the ddx of the second component minus the ddy of the first component times this third vector. Well, that's all very simple. That's just omega plus omega times k. So this is twice the angular velocity around this vector. And this vector field is for rotation in the xy plane. Omega is the angular velocity, and apparently the curl gives me twice the angular velocity as measured around this z direction, perpendicular to the xy plane. So we conclude, at least for this example, but this turns out to be general, that what factor did we pick up if we did the circulation? Well, we actually picked up a factor of, oh sorry, it was actually at the top, of 2 pi epsilon squared, or actually a factor of pi epsilon squared. And that is the area of a circle with radius epsilon. So I can rewrite this as the area of this circle times, all right, so the left-hand side here is a number. The curl is a vector. So how should I think about this? I can't write it like that, because then I still have this vector, k. But if I take the inner product of this with k itself, then essentially here I have k, I get a number, times k inner product with k, which is 1. Yeah. So, writing it differently, what is the curl of a vector field? It essentially measures the circulation of that vector field around that point per unit area, right? Because there's an area of that circle that I still have to take into account. And so the curl of some vector field f at a point P, when taking it with the inner product of the unit normal, that is, if this thing is tilted, then this is now seen to be this circulation integral per unit area of that circle that I'm doing the integral over. And again, here I could have also taken different things other than circles, and I would have different areas that I would have to look at. But this is my way of understanding that this curl thing actually measures something of a circulation of that vector field. Clearly enough for 1 hour. So let's have a break. Yes.
So the thing that revolves should replace the curl of p times k, or not? Because we were doing like this, we could do.
I've actually done exactly the same. So yeah, so this n, this unit normal is the k direction. But so the formula at the bottom also applies for situations where, so here I started with the xy plane, and I didn't do it in 3D, but in 3D, I could actually have something that is tilted in 3D, and now my unit normal could be something other than the z direction. Yeah?
Yeah, but so the area of the curl, the circle epsilon,
Yes.
that part's also within the.
It is, because that is, so this area here is now written to the other side, and there's 1 over the area. Yeah.